Good morning, students. How are you all feeling this morning? Are you happy or is something worrying you? Whatever it is, you are not alone. In your happy times, God walks next to you. And if you are sad or worried, you are not alone. Instead, He carries you in His arms. So just rest assured in His love. Shall we move on to today's lesson? It's a new chapter, Coordination Chemistry. In today's lesson, we are going to learn about what is a double salt and complex salt. We are going to learn about Oneness Theory of coordination compounds. We are going to see some important terms, and we are also going to learn about the different types of complexes and nomenclature of coordination compounds. Why is this chapter so important? Coordination compounds finds application in the field of medicine, in the field of catalysts. Most of the catalysts which we use are only D block elements or transition elements. Hemoglobin is a coordination compound of heme. Chlorophyll contains a magnesium coordinated compound, and therefore these substances are very, very important, and it is needed that we learn their structure and properties. First, let us see what are double salts. You know about simple salts which you studied last year. Every simple salt contains one cation and one anion. In double salts, there will be two or more cations and one anion. So let's see an example here. More salt. How to prepare double salt? Just take two simple salts, prepare saturated solutions, mix them well, boil them and allow them to crystallize. Here I have an example which is called as more salt or ferrous ammonium sulfate. As the name suggests, I mix ferrous sulfate and ammonium sulfate and allow it to crystallize. So what is the speciality of these salts? When you must have done salt analysis last year, like lead nitrate, chloride salt, calcium chloride, so many other salts, barium chloride, so many salts we did. So every salt contained one cation and one anion. But in double salts, you can see iron, Fe is one salt, ammonia is another cation. The anion is sulfate. So here I have ammonium sulfate and ferrous sulfate. So, but when I dissolve them in water, they don't stay together. I get ammonium ion, ferrous ion and sulfate ion. So, though it's a single salt, but when I dissolve them in water, I get three different ions. They just separate and go. Such a salt is called as a double salt. I have another example which is we all use potash alum. Padigaramnu solvanga Tamilla. Veedlalam kuda katti vittirupanga. It is a mixture of potassium sulfate and aluminium sulfate. So I take potassium sulfate, aluminium sulfate and crystallize. But when I dissolve in water, potassium goes separately, aluminium goes separately and sulfate goes separately. So such salts are called as double salts. But this chapter is all about complex salts or coordination compounds. What is the speciality? Here they have two ions. One is a simple ion and one is a complex ion. The one which I have written inside the square bracket is called as a complex ion. It will never split. You cannot expect iron to answer separately or thiocyanide to answer separately. It answers as one entity. Such an ion is called as a complex ion, and even if one complex ion is present, it is called as a complex salt or coordination compound. So this example is potassium ferrithiocyanate. Another example, tetramine copper 2 sulfate. So this one which is inside the square bracket, the copper and the amine together will never ionize separately. Sulfate is a simple ion which will come out. So the one which is inside the complex square bracket answers as a single entity and it is called as a complex ion. So even if one complex ion is present, it is a complex salt. The next we are going to see Oneness theory. Werner and his team, they tried to study the behavior of various complex compounds, and they were the first team to predict the properties or to explain the properties of complex salts. He took this compound as an example, hexamine cobalt 3 chloride, and started describing the properties. What did he say? He said the element has got two types of valencies, a primary valence and a secondary valence. So here cobalt is a central metal element. It has got two types of valencies, primary valency and secondary valency. The primary valency is positive and it is always satisfied by the negative ions. Actually, the primary valency is called as the oxidation number of the metal. Cobalt is the only metal in this complex. So that is always satisfied by negative ions. Here in this complex we are going to see cobalt is in the +3 oxidation state and is satisfied by the 3 negative chlorine ions, chloro ions. Then the secondary valency is satisfied by negative or neutral ions. What is secondary valency? The 6-amine is called as a secondary valency. The secondary valency corresponds to the coordination number that can be satisfied by negative, neutral or positive. In this case, the 6-amine are neutral in nature. But here when I look at this complex, there are only 5 amine but 1 chlorine. So 5 amine are neutral but 1 chlorine is negative. So the secondary valency can be satisfied by neutral, negative or even positive. Very rarely we have positive ligands. The next one, there are 2 spheres surrounding the metal ion. One is called as the ionization sphere and one is called as a coordination sphere. The one which just now we saw, the one which is written inside the square bracket, the metal ion and the ligands, the groups are called as ligands, which is written inside the square bracket, they are called as ionization sphere. They are very, very tightly held. That is why they never dissociate to give the ions in the solution. They always behave as one entity. That is called as the inner sphere or the coordination sphere. The 3 chlorine atoms outside, they easily ionize in water. They are loosely bound, here you can see by broken lines, and they form the outer complex or the outer sphere. The secondary valencies, this amine CH3 which is inside the coordination sphere are directional. They only decide the shape of the complex. The 3 chlorine which is in the outer sphere, they have nothing to do with the shape of the complex. So the 6 ligands which is inside the coordination sphere or inner sphere decide the shape. They are called as the secondary valences and they decide the shape of the complex. So for example, this is K4FeCN6. There are 6. It is arranged like an octahedron. Even though he was able to explain so many properties, primary valency, secondary valency, oxidation number, ligands, everything, he could not, Werner's theory could not explain the color. In your pyrotechnics, we use only these coordination compounds. He was not able to explain the color and magnetic property of coordination complexes. Next, we are going to study the important terms, many new terms we are going to study. Let's look at them. Coordination entity. By now you know so many complex we are seeing. The one which is written inside the coordination sphere is square bracket together is called as a coordination entity. So central metal ion, an array of ligands. There can be one ligand, one type of ligand or different type of ligands. So here FeCN6, this is called as a coordination entity. Fe is a metal ion, Cn is a ligand called as cyano. Then we are going to define the central metal ion itself. Usually the central metal ion is a d block transition element. Fe is a d block element. So the central metal ion which is inside the square bracket, CMI in short, okay, it is a d block element. It occupies a central position. Not only that, the main function of the central metal ion is to accept lone pair of electrons donated by the other atoms surrounding it, which are called as ligands. So since it accepts a pair of electrons, it acts as a Lewis acid. And these ligands which donate a lone pair of electron, 2 electrons, and they are called as coordinate covalent bond. Let's look at the structure to understand. So this is Fe, the 6 cyano ligands, each one donates a pair of electrons, and this is how we donate a coordinate covalent bond. You must have studied in 11th standard. So when I donate an aromatic, that means Cn is donating a pair of electrons to the ion. Next we are going to see what is called as coordination sphere. Again, the one which is written inside the coordination square bracket, which will not ionize separately as a together complex ion, is called as a coordination sphere. The central metal atom and the ligands together form the coordination sphere. So they are always written only inside what? Square brackets. So I have this example, potassium tetrahydroxyzincate. So this red color is once inside the red bracket is called as what? Coordination sphere. Here the central metal atom is zinc and the ligand, there are 4 ligands. Next, again coordination polyhedron. What decides the shape of the complex? Secondary valencies. Where do you find the secondary valency? Inside the square bracket. What else is there inside the square bracket? Metal ion. So the central metal ion and the ligands which decide the shape of the complex is called as coordination polyhedron. We have some examples here. So here both of them are 4 ligands. Okay, this is like a square planar. The same 4 ligands are arranged in a tetrahedron here. Let us recall the previous example, K4FeCN6. That will be like an octahedron. So the central metal ion and the ligands which decide the shape of the complex is called as what? Coordination polyhedron. Next, ligands, a very important definition, children. The group of atoms which is attached to the central metal ion, again where is it present? Inside the square bracket, is called as ligand. What is the main function of the ligand? They donate a lone pair of electrons to the central metal ion. Previously we saw central metal ion is a Lewis acid because it accepts electron, but ligands donate a pair of electrons, therefore they are called as what? Lewis bases. Let's look at the example here. I have CN, Cyano. Ones which are negatively charged always are named with an O sound. Cyano, chloro, bromo, like that. Now look at this complex. Guess how many ligands are there? Yes, nitro, aquo, amine. I don't call this as ammonia. To differentiate it from the ammonia gas that it is a ligand, we call it as amine, double M. I usually pronounce it as amine so that we'll write the correct spelling also. Because in organic chemistry we have amine, A-M-I-N-E. So there are 4 ligands here, 1 nitro, 1 aquo and 2 amine. Coordination number, quite easy but very important. The number of ligand which are donor atoms which donate a lone pair of electrons are called as what? Coordination number. So if I take this complex it is 6. If I take this complex it is 4. But let me have a different example for you. This is called as tris-ethylene diamine. There are only 3 ligands but I have written the coordination number as 6. Let's take a look. This one molecule is called as ethane 1,2-diaminoethane. This is ethane. 2 hydrogens are substituted by what? 2 amino groups. So there are 2 points of attachment. One molecule donates 2 pair of electrons to form the coordinate bond. So 3 molecules but each one is attached by 2 points. Therefore the coordination number is 6. Next we are going to calculate the oxidation number. The central metal ion, the charge on the central metal ion is called as the oxidation number. Now let us see how to calculate the oxidation state of the central metal ion. We know the central metal ion is always a metal which is a D block element and therefore it is always be positive in nature. Now while naming the central metal ion, we need to mention the oxidation state in Roman numeral right after naming the name of the central metal ion. Now let us see how to find out the oxidation state. This is a formula. Net charge is equal to oxidation state of the metal plus number of ligands into charge on the ligand. There are 3 types of ligands, positive, negative and neutral. Neutral ligands will not carry any charge, but a positive ligand and negative ligands will carry a definite charge. For example, you know oxide -2, all the halogens, chloro, bromo and iodo, they all carry -1 charge. Sulfato -2, carbonato -2, like that cyano -1, hydroxyl -1. So we need to know the charge of certain ligands which we come under common use in this chapter. Now let us look at an example. I have 2 examples here. First one, hexacyanopherrite. The charge of one cyanide ligand is -1. So now what is this -4? That is the net charge on the complex. So this net charge 4- is only equal to oxidation state plus number of ligands into charge of the ligand. Now let's substitute the values. So what do I get? -4 is equal to X. X is the oxidation state of the central metal ion whose oxidation I am calculating. Plus 6 is the number of ligand. As I told you, each cyano ligand has -1. So it will be X -6. Take 6 that side. So it will be what? Plus 6 and minus 4, it will be plus 2. Similarly, this is pentamine chloro. Amine ligand is neutral, it doesn't have any charge. But chloro, as I told you just now, has a charge of minus 1. So we have this plus 2 is the net charge of the complex. So plus 2 is equal to X plus 5 into 0y, because amine is a neutral ligand, plus chlorine 1 minus 1. So on substituting, I get the valency or the central metal ion charge to be plus 3. So we have learnt many important terms which are quite important. With this we come to the end of the lesson. Let's see what you've learned. Sorry children, we are going to see the types of complexes. Complexes are classified on two bases. The first one, they are classified on the basis of net charge they carry. As usual, positive, negative or neutral. If the charge is positive, if the charge on the complex is positive, then it is called as a cationic complex. So you can see here hexaamine. It is a cationic complex with a plus charge. Anionic complex, the complex carries a negative charge. Hexa, cyano, ferrate 2 minus 4. And some of them are neutral also. They don't carry any charge because all the charges are balanced. So I have cobalt, just now we saw plus 3. It is balanced by 3 Cl minus ions. So the triamine, trichloro, cobaltate. So here it is a neutral complex. Second classification is based on the types of ligand. If all the ligands inside the square bracket are of one type, if it's one type of ligand, then it is called as homoleptic ligand. That means same ligand is present inside. Look here, hexa aquo. The only ligand present is aquo or aqua. So it is only one type of ligand is present, or all the 6 ligands are same. Hence it is called as homoleptic. Heteroleptic. Hetero means different. Here you can see there are only 4 ligands, but there are 2 different ligands, amine and chlorine. Then it is called as a heteroleptic ligand. Let's discuss these. I have only amine here, 6 amine. Therefore this is a homoleptic ligand. And this one again homoleptic complex. But here again I have an amine and a chlorine. There are 2 different types of ligands. So therefore this is what? Heteroleptic complex. With this we finished today's concepts, children. So in this session, children, we learnt about double salt and complex salts, Oneness theory. We learned some important terms and the types of complexes. We could not go into nomenclature because that itself will consume more time. We will continue that when I have time later on. Revise the lesson and take up the test. Thank you, students. Stay safe.